Brace yourselves for a cosmic cataclysm of unprecedented proportions. Betelgeuse, the red giant star poised on the edge of our galaxy, is sending ominous signals through the universe. Using the James Webb Space Telescope, astronomers have uncovered something profoundly unsettling about this colossal celestial body. As renowned astrophysicist Brian Cox issues a grave warning, the question looms: are we on the precipice of witnessing a catastrophic supernova explosion that could forever change the night sky as we know it? Let's dive in. In the grand tapestry of the cosmos, where stars are born, live, and die in spectacular fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of immense proportions and age situated conspicuously in the constellation Orion. Its distinctive reddish hue and variable brightness have long been a source of intrigue, but recent developments have intensified interest in this celestial giant. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially monumental event in the life cycle of the star. But what could these changes in Betelgeuse signify? Are we witnessing the prelude to a cosmic spectacle of unimaginable scale? Betelgeuse, approximately 764 times larger than our Sun, is a stellar behemoth. Its colossal size is almost beyond human comprehension. Imagine a star so vast that, were it to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its stellar embrace. This incredible size is not just a test of Betelgeuse's physical attributes but also speaks to its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase characterized by expansion and cooling following a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8 to 8.5 million years old, is relatively young in human terms but ancient in the context of stellar lifetimes. Its current red supergiant phase is the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that have transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a story of transformation driven by the relentless forces of nuclear fusion and gravity. Ball's distinctive reddish hue is another hallmark of its current stage. The red color is a result of its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is about 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a red appearance. But this color is not just a visual trait, it provides clues about the star's physical condition and the processes occurring within its vast gaseous expanse. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese writings suggest that around 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a detail in the annals of astronomy but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It's a semi-regular variable star, which means its light periodically waxes and wanes. This variability is a characteristic dance of luminosity that has fascinated astronomers and skywatchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle along with a longer cycle that stretches about 5 years. These cycles have been documented as far back as 1836 by Sir John Herschel and possibly even earlier in Aboriginal oral traditions. But what makes Betelgeuse truly enigmatic is not just its changing brightness but its irregularity. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its colossal form. Recent groundbreaking revelation: Betelgeuse captured the attention of astronomers and stargazers worldwide with an unexpected and dramatic change in its appearance, an event now famously known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to mysteriously dim. The star's dimming was so pronounced that it began losing its luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, normally visible to the naked eye even in light-polluted areas, became markedly fainter, a change noticeable even to amateur observers. However, there's one problem with trying to monitor the activities of Betelgeuse: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists in the present but as it was in the past due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we perceive today left the star nearly 7 centuries ago. This time lag makes it challenging to predict and monitor sudden changes in a star's behavior as we are essentially peering into its past. The Betelgeuse dimming event served as a reminder of the inherent difficulties in real-time astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and the time paradox they introduce. The unfolding of Betelgeuse's celestial drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They utilized Hubble to analyze the behemoth star, a part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations offered a unique insight into the dynamics of a variable star like BLUS, which regularly expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated partly by the star's turbulent convection cells. Further analysis of the Hubble spectra taken at different points throughout 2019 and 2020 helped in measuring the movement of material in Betelgeuse's outer atmosphere. In particular, the spectra focused on magnesium SU lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of about 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, continuously loses mass, albeit at a rate far greater than that of our Sun. The scale of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, about 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and provide a rare opportunity to observe a supernova up close. Yet the question remains, what does this dimming event portend for BJ's future? Is it an indicator of an impending supernova or simply a unique episode in the star's long and complex life? Several theories were proposed to explain this sudden change. One prevalent theory suggested a phase in the supernova explosion process, a hypothesis that gained traction due to the common belief that Betelgeuse is nearing the end of its life. Another popular theory implicated dust, possibly from the star itself, obscuring our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud dense enough to dim the star's light from our perspective.